Chapter 3.5, Exponential Growth and Decay, and Modeling Data. So in this chapter, as I've said before, it's all going to be about modeling, about doing real-world problems, which we've seen modeling before, but now it's all going to be about exponentials, and sort of logarithms are going to come in to help us, but we're not really going to see so much logarithmic modeling. So, quick review. Remember the characteristics of y equals a0 e to the kt. So specifically, that is, it passes the horizontal line test, so it's 1 to 1. Its horizontal asymptote is at y equals 0. Its domain is all real numbers. Its range is 0 to infinity. Doesn't have an x-intercept. Its y-intercept is 0, comma a0. And you're probably wondering, why am I calling it a0 now? Or a subscript 0, which I will usually call a sub 0 or a naught, but a sub 0. Well, we're going to get to that in a moment. A sub 0 is part of our exponential growth or decay equation. We've seen exponentials. We've seen plenty of exponentials. We dealt with them with base b, and then we talked about base e, but that a sub 0 is very important when it comes to a specific type of them, which is the exponential growth and decay real-world problems. We now use the notation a subscript 0 to represent the initial or starting value of our equation. So notice in our graphing characteristics, we can see that the y-intercept right here is 0, a subscript 0. That's because essentially what we're saying is that the graph starts there when we're talking about real-world situations, where time starts at 0. So I don't really care what's going on over here. I don't really care what's going on over here. I care what's happening when I start time and go forward. So a subscript 0 just means the initial value of our problem, where we start. K is called the growth rate constant per unit time t. So if k is greater than 0, we have growth, and if k is less than 0, we have decay. So again, looking at these graphs, we're growing for k greater than 0, and we're decaying, we're getting less, we're decreasing when k is less than 0. Though this model uses e as the base, this does not always have to be the case. It's just the most common one, so it's the one we're going to mostly work with in these problems. We'll see at the end how to sort of transfer between them, though. So the population of India was about 1.25 billion in the year 2013, with an annual growth constant k equal to 0.012. If we wanted to represent this by a growth function, a model of this situation, how could we do it? So then, after we do that, we can project the population at a future date, provided that it's still growing at the same rate, which of course is maybe unlikely by 2031, especially with everything that's happened, but we can still use this model to sort of make predictions based off of previous data. So, we just need to fill in what is our initial value. What did we start with? We started with 1.25 billion. I'm just going to write 1.25 to make things a little bit simpler. And then we are given k, which is nice. We're not always going to be given k. So we can just plug in. We just replace our k and our 1.25. T is our x x in this problem. It's our variable. So we leave t there for now for our basic equation. Then e also, remember, e is just a number. It's just like pi. It's irrational. All of that. Do not replace e. E stays itself. Alright, so now we have this function. The population at time t is equal to 1.25e to the power of 0.012t. So to figure out what's going on in 2031, we have to figure out how does 2031 relate to 2013. So t equal to 0 is 2013. 2031 would then be t equal to 18, because it is 18 years after we started this. Because I don't want to be starting in year 0, literally year 0. I want to be starting in 2013. If I start this model in year 0, it's going to be very inaccurate, and also I'm going to get some insane numbers. If I plug in 2031, like directly as t, you're going to get an insanely large number that your calculator is just going to scream at you for. So make sure you're translating that time into something more reasonable to actually reflect the problem. So here we have t is equal to 18, so we take p of 18, and again, this is not something I expect you to be able to simplify on your own. This is what a calculator is for. So as I said before, in the previous types of problems, most of the time I expect you to leave it as it's like ln of a number or e to a power as your answer. Here, I actually want you to find the real answer, because if you tell me there are 1.25 e to the 0.012 times 18 people, that's nothing. That's not helpful. But for a real-world application problem, you should be giving me the decimal approximation, which is 1.551 billion. And once again, as I said in the exponents section when I introduced that should be very familiar equation that had to do with continuous compound interest, check that you get the same answer. Please take your calculator and try this in it, because when e is involved, some calculators get a little bit weird. Sometimes there's like weird orders you have to write things in to actually get it to work. So please do some practice, make sure you're actually getting the answers I'm getting, and if you aren't and you need help figuring out how your calculator works, now is the time to ask, not after the test is over. Alright, so let's see another example. In 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown to 180 deer. The population was growing exponentially. Write an algebraic function n of t representing the population n of deer over time t. So, since we weren't given a growth rate, we don't have k, instead we're going to have to figure out k for ourselves. So like I said, sometimes that's going to happen, it's not going to be so nice. So we'll need to take 2 points to form the equation. We will solve for k. So, point number 1 that we have is, well, the 2006, 80 deer. And the second point is 2012, 180 deer. So we can set t, once again, t is not going to be 2006 and 2012. T is going to be 0 if we start from 2006, and thus 6, because that is 6 years later. This makes our numbers much easier to work with. Again, you don't want your calculator screaming at you and giving you weird answers. If you're getting times 10 to the whatever power as part of your answer, you're doing something wrong. So, you get 0 and 80 and 6 and 180. Alright, so how can we use these? Well, first, since we have made time since 2006, that means this is our initial value. That means this is our a subscript 0. So in other words, we just get this. So we have n of t equals 80 e to the kt. So our only unknown here is we don't know what k is. We don't need to replace t, but we do need to have a number input for k. And so we can use our other point to do that. So I'm going to replace t with 6 and n of t, our output, with 180. So n of 6 equals 80 e to the k times 6, which equals 180 based on that point. And now it's something I know how to solve. So first I'm going to divide out the 80, because remember, we always want to isolate our exponent. Like so. I divide by 80, which 180 over 80 is 9/4. Then I'm going to take the natural log of both sides. So ln, which gives me k times 6 equals ln of 9/4. And finally, divide out the 6 to get k equals ln of 9/4 over 6. And once again, if you are being asked to evaluate this, it's kind of good to leave it in this form while you're doing calculations, just because then you'll have more exact numbers. But if I just ask you what is k, you can give the decimal approximation here. It's 0.135. Or etc., etc. 3 decimals is generally the amount that I'm looking for, because that's precise enough to get us pretty close to our answers. then I could graph this function and see what's going on. Just again, to check your work, that's one way to do it, is to graph it. Because a lot of these types of questions will be on the graphing calculator section, so it's a good thing to check with. So we can see 80 is, we're passing by 0, 80, and we are passing by 6, 180 like we need to with the given equation. Again, that given equation being n of t equal to 80e to the 0.135t, or more specifically, the ln of 9/4 over 6. So if you're not giving this as your final answer, you haven't actually finished the problem. Like if you just give me k, that's not the final answer. The final answer is that function. Now, a very specific type of problem you can run into is called a half-life problem. We're going to see a couple of specific types of problems that come up quite often. First, the half-life is the length of time it takes an exponentially decaying quantity to decrease to half its original amount. So this is something that is found a lot in like carbon dating fossils or artifacts, etc. So the half-life of carbon-14 is 5,730 years. If we wanted to express the amount of carbon-14 remaining as a function of time t, how would we do it? So this is what scientists use to figure out how old fossils are. First, we write a equal to a0e to the kt. So we start with our exponential. This is going to be a decay function, but they look the same. But this time, what we want to think about is specifically, we are decaying to half the original amount. So we know that if our original amount is A0, remember A0 is the initial amount, and we are decaying to half of that, that means we're outputting half of A0. So we replace A by 1/2 A0, and then we can replace T by the given half-life if you're given it. So in this case, right here, if our half-life is 5,730, and we replace this by half of A0. So remember, our goal in the end is to find K. So we go through and we solve for K. So to do that, I'm going to first divide out that A0. So I divide both sides by A0, and would you look at that? The A0s go away. That's always how that's going to work. Then I take the natural log of both sides. So natural log of 1/2 or of 0.5 is equal to 5,730k, and finally divide by 5,730k and I get, or by 5,730 and I get k equals ln of 1/2 over 5,730. So our half-life equation, if I am given a year, I can tell you how much carbon should be left. Or if I'm given an amount of carbon, I can tell you how old the fossil or artifact is. So this would be amount of carbon. This is the age. So this is how we would figure that out, is plugging in one side or the other. So for example, how many years will it take 40 grams of carbon-14 to decay to 10 grams? So if that's what's left over, if I know I have 10 grams left, and I know where I started from, well, I can go through and I can figure that out. So I plug in 10 as my new value, as my output, and 40 as my initial amount. Then I go through, I divide by 40. So when I do that, I get 1/4 equals e to the to that k value, I'm not going to read it all out, times t. I then take the natural log of both sides. Yes, I'm writing it as its decimal version just for simplicity. Then we divide by k, and I get this t value, which again, I would want you to present as an actual number of years, so 11,460 years. So if a scientist had something that should have 40 grams of carbon and now has 10, they could then state, oh, it's 11,460 years old. Now, one thing you can note about this is that there is a pattern to this. When you're looking for the half-life, k is always going to be equal to, like every time, it is ln of 1/2 divided by the half-life year. Like, that is the pattern. So you can also memorize that instead of going through this process, but be very careful that, if you memorize it wrong, then you're going to get everything wrong. So, but that is one thing we have, is that it's always ln of 1/2, from it being the half-life, divided by that year, 5,730. Next, we have what's called a logistic growth model. Now, logistic sounds vaguely like logarithmic. It's kind of related, but not quite. So this is not a logarithmic growth model or anything like that. This is its own thing. Essentially, what's interesting about logistic growth models is they have a second asymptote, which we've never seen before. Or a second horizontal asymptote, which we've never seen before. All of our rational functions, our exponential, our logs from before, we've only ever seen one horizontal asymptote show up. But for a logistic, we end up with two of them. So, logistic growth model is c over 1 plus a e to the negative bx. Our initial value ends up being c over 1 plus a. We can figure this out by simply plugging in 0, because that's what the initial value means. When I plug in 0, this just goes away. It's 1, so it's c over 1 plus a. Then c is called the carrying capacity or limiting value, and b is just some constant determined by the rate of growth, just like k was in the previous problems. So if I have, at time t equal to 0, there is one person in a community of 1,000 people who has the flu. This strain of the flu has a growth constant of b equal to 0.6030, and we want to estimate the number of people in this community who will get the flu in 10 days. This is generally how those models work. So you'll hear, especially now, you've probably heard about exponential growth of disease modeling. How disease modeling works, it is an exponential growth model where the amount of infected grows exponentially. But there's also this thing called a carrying capacity, which just means at a certain point, if so many people get the disease, it doesn't get passed on as much. It can't continue to live because they will no longer be infectable, so it won't have as many people to pass to. So the logistic growth ends up looking like an exponential at first, and then we reach this carrying capacity and we plateau. So we get that second horizontal asymptote at the carrying capacity. Our first horizontal asymptote is the one that is back towards negative infinity, and we get a different one towards positive infinity. So when we plug all of this information from the example into our equation, what does that necessarily look like? We can figure out first our initial value is at time 0 there is one person, so when I plug in 0 it has to equal 1, but remember that doesn't mean a is 1 this time, because our initial value is c over 1 plus a, or in other words 1,000 over 1 plus a, so a ends up being 999. So our actual model looks like the following, and then I plug in 10 for t to get approximately 294. So in 10 days, 294 people are sick. But at a certain point, as I continue on through time, up towards 1,000, once we get towards 1,000, we're not going to pass over that according to this model. So in the long term, this is where we run into this statement, the long term or the long run, or many years in the future, or many people in the future, whatever. Just the long run or long term is the words you want to think about. The number of people who will contract this particular flu is the limiting value c equals 1,000. So we get this specific graph where after 1,000 cases, which happens around day 21, no more people are going to get it. Like so. Our last type of equation that we can run into is called Newton's law of cooling. So the temperature T of a heated object at time t is given by the formula T of t, yes, big T of little t, is equal to capital C plus big T subscript 0, I know it's a little bit annoying that it's like that, minus C times e to the kt. lowercase t this time. So, how do we break this down? C is the constant temperature of the surrounding medium, such as the air temperature, the room temperature. It's whatever temperature, essentially this law of cooling just means how fast do things cool off. So it's going to be based on what the temperature of the room it's in, or the, if it's in the oven, or it's in the microwave, or whatever. Wherever it is, if it's in water, it's just the temperature of the substance that it is in. Then T sub 0 is the initial temperature of the heated object. That subscript 0, you can generally just remember that means initial. Like anytime you see a subscript 0, it just means the initial. It means when I plug in 0, this is what I get. And then K is some negative constant. It's always negative because we're always decreasing our temperature. That's just based on the rate of cooling. Once again, it's just some number that doesn't really have a context in the problem outside of once we plug in numbers, it gives us our answer. So, the steps to actually work on a problem like this. We have a cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit, i.e., the cheesecake is 165 degrees. That is ideal for cooking a cheesecake. It's placed into a 35-degree fridge. After 10 minutes, the cheesecake has cooled to 150 degrees. Find the cooling constant K. So step 1 is identify our points, just like we did before with the deer population. So we have points at our initial value is 165 degrees at time 0, and then after 10 minutes, so at time 10, we get 150 degrees. So those are our 2 points. We then substitute these in for any known substitute in any known values for the constant temperature or the initial value of T. So here, once again, 165 is our initial temperature, and the constant of the medium is that 35 degrees. The fridge, the air temperature within the fridge is 35 degrees. So that surrounding room temperature, 35 degrees. So we plug those in like so. And then I can technically simplify this a little, but I'll get to that later. We will use points to solve for the unknown values, just once again like we did with the deer population. So I go through and I'm going to plug in those points. So I've already dealt with the 0, 165, that's how I got this, but I haven't done anything with the 10, 150. So I plug in 10 for T, I set it equal to 150, and now I can solve. So I do some simplification. 165 minus 35 is going to be 130 e to the k times 10. So that 35 is still there, equals 150. Very common error that happens here is adding 35 and 130. Please do not do this. 130 is being multiplied by e to the k times 10. So they cannot be combined. Do not combine these. We just subtract off the 35 to get, what's that, 115 equals 130 e to the k times 10. And now we're looking like our typical exponential problems. I divide by 130, and we can see here how I've done this. So I divide out the 130, and I take the natural log of both sides, and then divide by 10. So I end up with natural log of 115 over 130 all over 10, which again we would simplify to a decimal approximation here. It ends up being negative 0.0123, which is a fun number. Notice, once again, it is negative the way it's supposed to be. If you have done this problem incorrectly, you will probably get a positive number. So just remember, we are decreasing. Our temperature should be decreasing, so our K value needs to be negative in order to make us decrease in value. So if you plug in, please check your answers on these. Like, I cannot stress that enough, that simple algebra mistakes, or plugging into your calculator wrong, but it feels right because, again, some calculators are weird about how you have to plug in logs and e, etc. can really just lead you down the wrong path when if you just check your work, if you plug in the points, plug this point into your final equation and make sure it actually works. So anyway, our final equation would have been this equation, but with k plugged into it. Alright, so the last couple topics for this chapter, really for this whole unit, are going to be how to choose a mathematical model in the first place. So when faced with a bunch of data points, we don't always know what model is best when we just look at them. So if you're asked to figure out whether you want a linear or an exponential or a logarithmic or even a logistic model, which again, we haven't really looked at logarithmic models, but we know what logarithms should look like when graphed, so we still can make logarithmic models. If we want to know which model we want to use, it's going to be based on the relationship between the points. Your best bet is always just to graph them in general. So when I graph them like so, I can see there's a curve to it, right? So clearly it's not really linear. Yes, you could make a linear approximation, and if you've taken any sort of like statistics course, etc., you would know how to find a linear regression equation, even if it's not perfectly linear. But, well, linear is probably not our best bet when it's curvy like this. Also note that our graph is concave down. So in this case, that actually does imply logarithmic. So remember that exponentials look like this or like this, right? Well, not crossing that way, but that's exponential. This is your e to the x or your b to the x. And this is your b to the x when it's a negative number. But this is not either of those things. And there's clearly, at least not from what we can see, there doesn't appear to be any sort of carrying capacity. There doesn't appear to be any sort of horizontal asymptote, so it's not logistic either, no carrying capacity. So that concave down shape that the logarithms have, even if it was this way, which is not concave down, it's concave up, but if we had that, then, well, we can say this looks logarithmic. So our equation should be y equals some number times ln of some number times x, or something like that. Maybe there's more going on depending on how it's shifted, but right now it's got that point. It's got that special point that we always have to remember that's 1, 0 point, so it doesn't seem to be shifted anywhere. So we just plug in a point that we were given. Like 1, 0, I can do that. When I do that, I get 0 equals a ln of b, which means ln of b equals 0, so b equals 1. And then plug in some other point. Again, taken from right here. I'm plugging in the last point we had because that helps a little bit. And we get a is approximately 2. And so we could approximate this with y equals 2 ln x, which is actually the exact formula, but it's not always going to be exact. So in general, you won't be necessarily asked to find exact regression equations or anything like that you would have to do in a statistics class, but understanding which type of model we're looking at, which just means which type of graph are we looking at. What is going on? When I graph this, it looks logarithmic. You need to be able to recognize a logarithm versus an exponential. Which one is which? Is there a carrying capacity? So is it logistic? Is it a straight line? Is it linear? Recognizing those types of graphs is going to be very important. And our final topic is how do we change to base E? So you'll notice all of the types of models we looked at in this chapter had base E, but that's not always how things are going to be given. There's plenty of times where you could be given a situation where the base of the function is not base E to begin with, and that's totally fine. The only reason we use base E is because it has some nice properties in calculus and such, which again you'll see when you go there if you move on to calculus, but for right now we just want to know how do we get it into that nice format. So first, we use our properties of e and its relationship to the natural log. So we rewrite y equals a b to the x as y equals a e to the ln of b to the x, which seems pretty weird, but remember that e to the ln, they cancel each other, so that's just the same thing as b to the x. Like so. So if I have this equation, 2.5 times 3.1 to the x power, and I'm trying to write it in this nice base e format that we like so much, all I would need to do is rewrite that e to the ln in the middle. So e to the ln of 3.1 to the x power. Then we use the power rule of logs to rewrite it in a slightly nicer format. So this x can be moved outside, out front of the ln, like so. X ln of 3.1. ln of 3.1 is something I can plug into my calculator and get a numerical form for if we need it, or you can leave it as ln of 3.1 to be a little bit more exact. So note that a, in this case, is the same thing as the initial value. It should stay the same the whole time. And k is simply just going to be ln of b. So you can memorize that directly and just rewrite it as a e to the ln b times x. And that's it. And so that's it for this unit, in fact. So once again, my biggest note for this unit is please try some of the practice problems I did in here and make sure your calculators can do them. Make sure you know how to do them on your calculators, because there will be a section where you will have to work with a calculator to simplify exponentials, and that can go very wrong. So please check that you know how to do it before you go to take the test.